Question 4, the first part, just like question 1. Same shape of the graph. Again it says show numerical values on the n-axis. And we'll quickly check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, so you can fit 120 neutrons up that axis. Slightly different from question 1. Question 1 asks for the regions where the particular sorts of decay occur. Here it says indicate a possible position for a nuclide. So this would be just one little cross that's in the zones. So one little cross in the alpha zone, one in the beta minus zone, one in the beta plus zone. Part C tells that this isotope radon decays sequentially by emitting alpha particles and beta particles. In other words, it emits alphas then betas and in any sort of order, one after the other. Eventually you're getting an isotope of lead. 4 alpha particles are emitted in the sequence. Well, we know that every time you emit an alpha particle you're losing 2 protons. So it must lose 8 protons from the radon. So if it loses 8 protons, it started with 86 of them, you can work out how many protons you'd end up with. But the final product has got 82 protons. So in order to get from the number of protons that you've just worked out there up to 82, you have to remember that every time a beta minus is emitted, a neutron becomes a proton. So you should be able to work out from all that, if the 4 alphas effectively take away 8 protons, but at the end of all this chain of decay the number of protons has only gone down by 4, you can work out how many betas there must have been in the sequence. Part D, a particular nuclide is proton rich. In other words, it's got too many protons to be stable. Discuss 2 ways in which the nuclide may decay. So it says discuss, so don't just name them, but say what happens. And the mark scheme actually gives 4 options of things that can happen. There's beta plus, there's alpha decay, there's proton emission, and there's electron capture. So you can choose any 2 of those and explain a little bit about how they happen, or why they happen, or why they might be unlikely to happen, and how them happening gives you greater stability. Question 5 is about electron diffraction. So you shoot a high energy electron beam at a sample and you get a diffraction pattern caused by the nucleus. So the first thing to do, on the axis below, sketch a graph of the results expected from an experiment where you're moving a detector to different angles and you're detecting how intense the beam of electrons is there. And the critical point about this is that the straight on direction we've got high intensity, but then just like with light, when we've got the pattern of rings, the intensity drops down to a minimum. And that's the key thing that the mark scheme is looking for. In fact, you've got a minimum, and all it says about the minimum is that the minimum won't be 0. It doesn't then matter too much about what the graph does after that. Think about the rings of light. You would get other maximum minima later on, but we're not bothered about that. It's only the first one we're interested in. State why high energy electrons are used in determining nuclear size. Well, if you realise, as it explained at the start of the question, this is an effect of diffraction. Diffraction, of course, is all about waves. So although we're using electrons, we're thinking of the electrons we're using as being waves, de Broglie waves. Now, if we know about diffraction from diffraction of light, we know that you only get significant diffraction if the size of the obstruction is about the same as the wavelength of the waves. So if we want to get diffraction around a nucleus, we've got to use waves whose wavelength is about the same size as the nucleus. Very high energy electrons behave like waves with very short wavelength, about the wavelength of the nucleus. So by using those we're able to get a diffraction pattern. And it tells us that electron diffraction experiments have been used on all sorts of nuclei, giving us information about the nucleus. And we came to a conclusion about the density of all nuclei. So you need to think about what was the conclusion. What do we know about the density of all nuclei? And related to that, what do we know about the average separation of particles in big nuclei compared to the separation in small nuclei? Sketch the relationship between the radius of a nucleus and its nucleon number. Well, if you've got the data sheet to hand, you'll see that the equation is given. R equals R0 a to the third. And this asks you to plot R and to plot nucleon number. So we're not going to expect to get a straight line graph when we plot those two things, because there's the equation. It's like a power of a third graph. So we know it's not a straight line. If it's not a straight line, it's going to be curved. It will either be something that curves up like that, getting steeper, or something that curves up like that, getting shallower. We've got to guess which one it is. And I know that if the equation was something like r equals r naught a squared, a graph of y is x squared is one that curves up. So if the power was more than 1, I'd expect it to be like an x squared graph and curve up. Because the power is less than 1, it must be the other way around. So this graph must be that sort of shape. We could put some values in to do it a little bit more accurately, really. Because we know that in order for the radius to double, a to the third has to double, which means a has to get bigger by a factor of 8. So I should actually have used that to help me get the curve a bit better. Right, part E. Given that the radius of a carbon-12 nucleus is that much, how would you find the radius of a different nucleus? Well, there's the equation. R equals r naught a to the third. And that works for any nucleus. So one way of doing it is to put in the values for the carbon-12. We know what r is, we know what a is, so you can work out what r naught is. And when you know what r naught is, you can then use the equation again and put in the data for the oxygen. You know the value of a for oxygen, you can work out a to the third, multiply it by the value you just worked out for r naught, and then you've got r. That's one way of doing it. If I was doing it myself, I'd probably do it by ratio. I'll leave you to take your pick. Question 6, following straight on from the same topic that's on question 5. R equals, it doesn't call it r naught this time, just because capital R equals little r a to the third, but normally we call it r naught. It lists some values of r and a. Use the data to plot a straight line graph and use it to estimate the value of r. So since r equals r a to the third, if we want to get a straight line graph, we could plot r on our y-axis, on our x-axis we'd plot a to the third, and what would little r be? Well, y equals something times x, that's going to be the gradient. Notice, by the way, that we don't get involved in doing log graphs at this point, or log graphs, because we're told what the equation is. If we'd got the data and we didn't know what the equation was, then we might start doing log graphs. But here, when you're told a formula, you've got the numbers to put in. It's just a matter of spotting how to make a straight line graph. So that's what we'd plot. Hope you've got some graph paper at home. If you haven't, you can always go to graphpaper.com. There's some websites where you can print off your own graph paper if you haven't got any. Finding the approximate density of the nucleus, it's relatively simple because you've got a load of nuclei, you know the radius, so you can find the volume, you know the number of nucleons, you know the mass of one nucleon, so basically for any of those 5 nuclei you can find its mass and its volume and calculate the density. The trouble with doing that is you probably get slightly different answers whichever one you used. There is a way of using the results of your graph and using that to find the nuclear density, and that is a much better way, so see if you can sort that one out. It says state the assumption you make when you find the density. Well, there's all sorts of things that we assume. Some of them we don't even realise. The very fact that we're dealing with nuclear radius means we're assuming that the nucleus is a sphere. We ignore the gaps between the nucleons. We assume that all nuclei have got the same density. We assume that the mass of the nucleus is the sum of the mass of all the different bits, which is something we're going to see later on might not necessarily be the case. So there's plenty of assumptions, you've just got to state one of them. And for those of you who are up to the challenge of trying to find the nuclear density using the value from the graph, here's the arguments that you have to use in order to find it. Where m is the mass of a particular nucleus, that's capital M, little m is the mass of one nucleon. I'll leave that for you to try and work your way through to sort out what's going on. Question 7, well, you may recognise this. It looks very much like question 5 to begin with. Sketch a graph to show the results of the diffraction experiment. Well, we've just done that for question 5, so I'm not going to do it again. You can do it again. It's all good practice for you. The next part of question 7, you got some data. Ask you to plot a graph to confirm r equals r naught a to the third. Well, that does sound very much like what you've just done for question 6. So that should be straightforward. How do you estimate r naught from the graph? Well, you've just done that for the previous question, so do it again for this. Discuss the merits of using high energy electrons to find nuclear radii rather than using alpha particles. There's all sorts of things that you could say here. For instance, we did mention that with alpha particles you don't actually measure the radius. All you do is you find out a value and that you can say the radius has to be less than this value. If you haven't found the radius, with electrons you can. That's one of the possibilities. There are lots of other things. The mark scheme's got 6 points, you've only got to find 3 points. So that's something for you to have a look in your textbooks about. What the advantage of using high energy electrons.